Right, let me show you how to answer some questions, exam questions, to do with forces and matter. It's only a short chapter, there's not that many questions come up every year per paper. With 13 marks, this came from 4 papers. It's about 3 marks per paper, which is still half a level. So let's make sure we get some practice done here. Question 1. The graph in figure 14 shows the variation in atmospheric pressure with the height above sea level. Now this is actually triple. However, the way they've got this question and this question, it's just data handling. The only triple part of this question is actually this, part 3, triple award. So let's get question 1 and 2 done. Use the graph to estimate the atmospheric pressure at 3,000 metres above sea level. So this is just a data handling question. Here's the data, can you handle it? So 3,000 metres of height and the corresponding pressure is 70 kilopascals, correct. Part 2. Use the graph to estimate the atmospheric pressure at 6,000 metres above sea level. So once again, height above sea level, this time 6,000 metres. Come down here like that. Right, I don't know, that's 40, that's 50. What, it looks about 47 to me. If you were interested in this question, suggest a reason why the atmospheric pressure decreases with height above the sea level. Well, if there's the sea level and there's space, look at all of those air molecules above your head. So if you're there, there's a lot more air pushing down on you. So the higher you go, there's less air pushing down on you. But like I say, that's triple. So you don't need to know it if you just combine science. Question 2. A weight of 4 newtons is used to extend a spring. The extension of the spring is 0.06. So X is for the extension and that's your force there. Calculate the spring constant K. Use this equation. Right, so we're going to need to rearrange it. So magic triangle, divide by sign, times by sign, to create 3 boxes. I've got something times by something, and I've got space for something times by something, so pop those in. And I've got a 1 box left and 1 thing left, so shove that in there. Cover up what you're looking for. We're looking for the spring constant K. So that's F divided by X. Pop the numbers in. And that equals 66.67. So I'll put it to 2 decimal places because that's to 2 decimal places. Part 2. State what measurements should be made to determine the extension of the spring produced by the 4 Newton weight. Right, so at first you've got the spring with nothing on it. So that is the original length. Then when you put a weight on it, it gets longer. So that's the final length. And then to get the extension, it would be just that there. So the final length, take away the original length, and that'll give us the extension. And that'll get 2 marks there. So you just literally needed to put this. You didn't need to put any other pictures. Question 3. Another spring has a spring constant of 250 newtons per metre. So that's K. Calculate the work done in stretching the spring by 0.3 metres. So that's extension. Now they have said work done, but the equation they've gave you is E. Well, remember, E equals energy, which also equals work done. So they're just basically asking you to work out E there. So we'll just pop the numbers in. A half times by K was 250 newtons per metre. Now let's just make sure, have they gave us the extension in metres? Yes. So they might have gave us it in centimetres, in which case you would have to remember to convert it. Now remember, that needs to be squared. So you do the squared bit first. So popping that into your calculator would be 0.3 squared, and then just times it by 250, and then times it by 0.5. And that comes out as 11.25. Now they want to know the units as well. Well, the units for work done, well, if work done equals energy, all energy is measured in joules. So make sure you know that for an easy mark. Question 4, the last question. Figure 9 shows a 10 Newton weight hanging from a spring. One of the forces acting to stretch the spring is shown in figure 9. Complete figure 9 by adding an arrow to show the other force acting to stretch the spring. Right, so 10 newtons is pulling the spring up. We just need to know how many's pulling it down. Well, it'll just be the 10, won't it? We just need to draw an arrow. So the arrow should be the same size but opposite in direction. And it should act, really it should be acting there. But if you do it from the weight as well, that's fine. So you're looking for equal size for 1 mark and opposite direction compared to the original force up there for 1 mark. Now this chapter is about springs, and there is something that's being missed off, and that's what the graphs look like. So just as a little masterclass down here, if we do force extension graph, right, for a spring, it's going to be linear at first, and then it'll get to what we call the elastic limit, and then it'll go curved. So that's for a spring. And you're also supposed to know the force extension graph for a rubber band. So that'll be curvy at first that way, then it goes curvy that way. And for the spring, this section here, what we see is that extension is directly proportional to the force. Now remember, for anyone that's been following all my past papers here, remember directly proportional means if one thing doubles, another thing doubles. So what you might see is a force extension table. If the force is nothing, the extension's nothing. So if I double the force, it's doubled the extension. Or if I treble the force, it trebles the extension. Do you remember that? But for higher values, it won't follow the same pattern. So say once it gets to 7, instead of going up by another 2, it might go up by 3. And then it might go up by 4 on top of that. Right, so now I feel quite confident that we've covered that chapter quite well. Okay, good luck in your exams. Work hard and be nice.